I'm going to talk about deep and multi-fidelity learning with Gaussian processes. And this has two parts, deep Gaussian processes and multi-fidelity learning. And eventually, I'm going to show basically how you can use the same model, deep Gaussian processes, for multi-fidelity learning, somehow fusing both of the ideas. And I was not exactly sure about the audience, so I was thinking that for a 30-minute talk, I could do a specific topic and kind of drill into that, or I could cover a little bit more things for deep GPs and be a bit more high level. I opted to do the latter. Hopefully, it's going to satisfy you, but feel free to interrupt me and make questions in case you want to drill down in one of the specific topics, right? So yeah, I'm happy if you raise your hand to answer questions during the talk. Good. So I just want to say that various parts of this talk come from work with a lot of people, but at least here, Kurt Kutajar, Paris, Perdikaris, Mark Poulin, Javier Gonzalez, Neil Lawrence, and others. And to start with the first part, the deep Gaussian processes, I'm going to show kind of a schematic here. This is the depiction that you usually see in more neural network-like papers, and I think this is the graphical models that we like to use in the Bayesian literature. And I'm going to use this throughout my talk. The reason I'm putting also this schematic here is because you have the word deep there, so you want to somehow show how that really this is a deep learning model, right? So in a deep learning model, you have your inputs, which I denote with X, and you have your outputs, if you do regressions like continuous variables, Y, and then you learn a hierarchy of hidden layers that learn to map the inputs to the outputs, okay? And if I compress everything such that all these multiple dimensions are denoted by capital letters, I have also this depiction here. And I would like to think about this in the function space using Gaussian processes. And in this sense, you could imagine that every mapping between every layer is a function, and I model it with a Gaussian process. And this is giving you this kind of nested formulation, right? So your output Y, is it OK if I'm moving with the camera? Yeah. The output Y is going to be basically a warping function of the warping function F2 and so on until the last warping function F1 that is acting on the input and so on, OK? And the properties of the Gaussian processes, I mean, you can see that I didn't even write mathematically what it looks like, right? It's like very simple. You literally create this nested composition, you pass one function into the other. How to do inference is a different story. It's kind of complicated, but I'm not going to speak about this for now. So instead of having the traditional Gaussian process where you go from inputs through a function to some outputs, you're going to have these intermediate spaces. In neural networks, people call it feature spaces. Here I'm calling it latent space. And what you get is that you get a deep structure with non-parametric nonlinear mappings, as opposed to deep neural networks, for example. The mappings are marginalized out analytically, as you do when you do Gaussian process inference, right? And the end result is not a Gaussian process, right? So you get something that is different, it's like non-stationary, and it's not a Gaussian process. It's a different process, right? So here is the objective of the model. So you want to learn the marginal likelihood. And to do that, as I said, you want to integrate out all the layers. And the instantiation of the layer I denote with this H, right? And the mapping I denote with F, right? And you see that here you have like the nested composition. And if you get, so you have, if you start with one layer, which is like this blue H2, so sorry, I forgot to put here the index. This would be H2, this would be H1, right? No, sorry, it's the other way around. That would be H2, right? So if you get like one layer is the standard thing that you would expect for Gaussian processes with also having the latent space that has to be marginalized out, right? So that's kind of a latent space, a Gaussian process with an intermediate latent space, right? So you have H1 given X, and then you expand with a function, so F2 given H1 and so on, right? And you want to do this in a nested way, which means that to do inference for the second layer, you need to pass the whole marginalization of the first layer, and so on, right? So the more layers you add, the bigger this integral becomes. And I'm going to talk about it maybe a little bit later, but passing samples obviously is easy, right? But here you have integrals because you're going to propagate a certainty, right? You don't want to propagate samples, you don't want to propagate gradients as what people do in deep learning, right? So you're going to propagate a certainty, and that's how these integrals arise, right? So you marginalize the latent space and the mappings, and this is giving you this headache. Okay, so far. I'm just going to talk about the properties of the deep GPs now in graphically. And I hope it's clear how you get a deep GP, right? You literally stack one GP over the other, right? You write the objective, and then the whole point is about how to do inference, right? But drawing samples is easy. You literally sample from one GP, right? And then you take the sample and you throw it to another GP, and then you do that in the last layer where you have your output, right? The whole point is how to find the posteriors for the mappings in this way. Is that clear? Is that confusing? Right? Yeah. Good.
But let me ask something. So
yeah.
You have that first layer. Now you can have places that have very different x's
Mm-hmm.
that have very similar outputs from the first layer.
Yes.
Now you put that into another layer. Well,
yes.
then that's going to have a similar output.
Yes.
At that point.
Exactly. So that's exactly the point why you could do that. It's of course you can imagine that this is going to give you something that can work in certain cases, right? So the motivation, right? Why you could do that? I know it could be a bit confusing, but it's part of the motivation actually, right? So imagine that you want to model this kind of functions here, right? And as you have a continuous input. Let's say its time is 1, 2, 3, 4, 5, 6, right? Which I just show with a line there, right? And you want to model these functions, and then you see that these functions, they have like some, there is some mirroring effect here, right? Like there is, how's it called? Not mirroring, like symmetrical. Yeah, sorry. There is some symmetry here, right? So you see that this area here has symmetrical outputs, right? And this area here has this symmetry again, right? So you see that if I put an axis here, there is a symmetry here. There is a symmetry around here. There's a symmetry around here. And moreover, you have different frequencies. So you see that here there is much more wiggly functions as opposed to here that is much smoother function. And you also have long-range correlations, right? So you have things here that correlate with things here. So if you want to model something like that, right, you can come up with a very, very sophisticated kernel. But what you could also do is do exactly what you mentioned, which is like, well, I know that there is a symmetry around this area and this area of my input space. So by having intermediate function that's warping my input space, I take this area here and this area here. They map to the same value, and this constrains my output to also have the same value. So I learn symmetries in this way. And the other thing that I learn is like if this intermediate function is changing rapidly, this translates into a wiggly function in the last layer. If this function doesn't change at all, right? So I have something very smooth in the last layer, and so on. So you learn this kind of features, right? So yeah, is that clear? So it's part of the motivation, basically, is how to learn features. I was planning to not talk about this slide. We can come back to that later, but it explains even more how the features are found. So here's another example showing what you can do with deep Gaussian processes. So imagine that you have like a step function. It's on the board there. So you have a step function, you have observations in 0 and 1, and you are fitting Gaussian process, and of course it cannot capture the discontinuity, right? And that's the Gaussian process fit, and the red shades is the samples. I took many samples of the fit. And you see there is a few problems, obviously, right? So the single length scale in the Gaussian process cannot cope with the small variations in the observed data, as well as the bimodality that you have in the two clusters here, right? And also, of course, away from the data, you revert to the mean. So you see most of the samples are 0, right? And of course, here in the discontinuity, strange things happen, right? you cannot even interpolate from some of the points around this continuity. So what happens if you do a deep Gaussian process, if you apply deep Gaussian process? With 2 layers, you get something like that. And with 4 layers, you get something like that. So what it shows here is that, firstly, the model has capacity to fit this data, as you can see here, right? And to model the individual noise here in these clusters as well as the bimodality. And the other thing, which is the most striking thing that you observe here, is like away from the data, you learn basically posterior, that is understanding that you have these 2 different regimes, right? So if you take the mean, of course, it's the same mean. It goes to 0, but the samples are learning to do these jumps. So and you can think of it as having a Gaussian process whose prior is another Gaussian process, right? So at least that's how I'm thinking about that. So here you have a Gaussian process whose prior is another Gaussian process that learns some warping, and that's why away from the data you get some convergence to the mean, but in this case the mean is something much more complicated, right? And you see that with more layers you get much fewer samples falling in between, almost nothing basically.
Do individual realizations show extra jumps? Because this is only showing the marginal distance.
Yes, I'm going to show it in the next slide actually. So individual realizations look like that, and to reach that I'm going to start from the beginning and show that in the first layer you get your input and you learn a warping function like that, right? And of course this looks much more similar to the single layer GP, right? But what's happening is that successively the deep GP is warping the input in a successive manner such that this input now goes here, this goes here, so that in the last layer where you have the observations, the overall process is getting samples that have this probability of jumping without the smoothness in between, right? So you can see, I don't know what color is easy to see, maybe the blue. Everything has to fit the data, obviously. It fits the data, and then with some probability you have like these jumps that decides to go to either the 0 or the 1 regime, right?
It's very interesting. Would you say, I mean, obviously extrapolating is a very hard game. Would you say that extrapolation therefore is better, or would you say in some sense poor?
Right, so when I did these plots, I took for granted that extrapolation is better because it fits with intuition. But then in my PhD defense, I got this question, and the reviewer argued that might not be the case. And I'm not actually sure. So it was like Rich Turner, right? And he asked, is it actually better? Well,
Sounds like a very smart guy, isn't it?
He's a very smart guy. So I'm not sure, to be honest. I think in the end of the day, that's why I like to think of it as a GP with another GP prior, because I'm just saying that this is my prior here, and I'm sure someone can argue that so far from the data, maybe that's not the reasonable thing to do, right? I think that it makes at least it demonstrates something, right? It demonstrates that it can learn a completely different prior, right? It can learn this bimodal regime, right? But I agree with the point. I don't have the perfect answer to that. So here I'm going to show some more complicated example. And again, I will not go into the details, but here's how you do unsupervised learning from multiple views. And I put this here just to show that you can use deep GPs to do complicated feature learning in the same way as people use deep neural networks, for example, right? So you can learn complex dynamical structures in this case. So, and also from multiple views of the data. So in this case, I had 2 data sets, and each data set is a time series, and each time series represents one of the 2 subjects here, and the subject is basic, and the motion is 2 subjects. They walk towards each other, they do a high five, and they walk away. And I want to model this temporal evolution in these 2 data spaces of the 2 subjects with a deep Gaussian process. So Y1 is the time series for the first subject, Y2 is the time series for the second subject. And you can actually do purely unsupervised learning here, but I'm not going to discuss about that because it will take a bit of background. And let's imagine that here what you do is like regression, where you regress from time, time could be like the frame of the motion, right? So that's like t1, t2, t3, and so on. So you regress from time to the high-dimensional output of the motion capture data that you have here, right? And I want to do feature learning and hierarchical function learning because I know that there is some common phenomenon that should be captured by the two functions because they do very similar interacting motions. And what I see, imagine that you have like time as input on the top. I didn't have it here. Again, it would be like the straight line like before, 1, 2, 3, 4, 5 until the number of frames that you have, right? So I learned a two-layer deep Gaussian process. I'm going to explain exactly what we see here, but if you focus on the first layer, that's like the feature space that you learn when you warp the time in the first layer, and it looks like kind of a circle kind of thing, right? In 2 dimensions, so it's 2 dimensions, and I plot one versus the other, right? So it looks like a circle, and this is because these subjects are doing some sort of periodic motion. So they walk, they high five, and then they keep walking. So the start and the end of the motion is similar. So here's probably where they do high five, and the start and the end of the motion is similar, right? That is not completely close, but what you learn in the first layer is that you want to warp the time such that when you learn the function, the start and the end of the motion are similar. And then what I did, I put one more layer, and I'm not going to fully explain, but in this layer I have many dimensions, and I have a way of understanding which dimension. Well, I can tell you in high level, of course, you use automatic relevance determination, covariance, right? And this allows you to understand which of the dimensions of the second layer are relevant for this data set, and which dimensions of the second layer are relevant for the other data set, and which are relevant for both of the data sets. Okay, so I learned a multidimensional function, and I plot here the instantiations in pairs. And given the other information that I told you I have, I know that this pair of dimensions is relevant for both of the subjects. And you can see again this kind of circular pattern, which reflects kind of the dynamics. And the other, and I can actually verify that by sampling from this space, right? So I can pick a point here and then sample, and then I get something like that, right? So if I pick a point here, I get these samples. If I pick this point, I get this sample, and so on, right? And the other two feature spaces that I plot here as pairs, they are private, and they model the slight variations that the subjects are differing, right? So they're not doing exactly the same motion. It's literally 2 different people with 2 different walking styles, right? So that's how I did feature learning with a 2-layer deep Gaussian process. The commonality is represented as this 2-dimensional feature space that has this periodic circular pattern as you would expect, and the non-common features are represented as some completely different private space, and they capture basically the particularities of how each subject is working, right? As I said, you can do this in a completely unsupervised way, which I think is not possible to do with neural networks, right? Because you don't have a Bayesian training procedure, it's not going to work. Okay, and I am going to jump to the, let me see the time, sorry. Yeah, so that's for the deep Gaussian processes. I was planning to conclude the section about deep GP so that I can talk about the multi-fidelity in the next 8 minutes or so. And if there's questions, I have some backup slides here that I can discuss. Oh yeah, that's what I want to mention before, right? That the problem with deep Gaussian process is how you actually do inference, right? Because you have to propagate uncertainty from a nonlinearity, because the mappings are nonlinear, and that's extremely hard to do. And I just want to mention briefly that I think the state-of-the-art ways to do that is with variational inference, Monte Carlo, EP. Okay. Yeah, if there's questions, I will come back to this slide deck. Now I'm going to jump to multi-fidelity modeling that was briefly mentioned in Michael's talk. So here is kind of my understanding about multi-fidelity. Imagine that you want to do, to predict the weather or something. So it's not my domain, so I have like a very simplistic view here. You're going to predict the weather. So you have some high-fidelity observations from this, fancy sensor. And then you have some low-fidelity observations. Maybe you have like some wearable that, senses humidity. I don't know, right? And these are low-fidelity observations because, of course, the sensor is not giving you as good data, but the point is that you can get maybe much more data, right? And the same with simulations. You can have high-fidelity simulations, and you can also have low-fidelity simulations. And the difference would be like, the low-fidelity simulation, you do like very rough approximations, and the high-fidelity simulations, you solve the numerical problem as close as possible, but of course, it takes ages, so you have much fewer data. So the question is how you can get like the good data and the bad data come from the different fidelities and fuse them all together, even when it comes to like real data and simulations and everything together, right? So here I'm showing how we did that with a variant of deep Gaussian processes. And here what you see is that you have a high fidelity function, which is the red function. It's toy data, of course. And there is a low fidelity function, which is the blue function. And you get observations only where you have the dots. So for the high fidelity function, you don't have any data here, for example, right? For the low fidelity function, you have much more data. And the question is how you go about learning from this data, right? Of course, if you just take the high fidelity data into account, or even some sort of naive combination, your predicted high fidelity is going to be this green line, which basically says, well, I don't understand what's happening because I see like a few data points down there, a few data points up there. It's giving you the mean with huge error bars, right? What to do with our model instead is managing to interpolate almost exactly the true function, which is the red. And even in the areas here that you have no data, you can interpolate it and also get reasonable confidence intervals that say, well, that's what the function is probably, but I'm not exactly sure because I don't have high fidelity observations here. And why you got this interpolation here is because you do have low fidelity observations, right? And this can still tell you something. So the whole point is that we want to trust the high fidelity data where you have them. And when we don't have them, we want to see the low fidelity data and the reason how the high fidelity data would look like, right? And here's a model that has been traditionally used with GPs to solve this problem. So the high fidelity function is learned based on the low fidelity function that is scaled by some constant or some function, plus some other Gaussian process that is learning, I have 2 minutes left. Okay, that is learning the bias between the different fidelities. Okay, is there a question? Okay, no. That's learning the bias between the different fidelities, right? So in essence, what you do is that you can imagine of that as having as a high fidelity function that learns to revert to a warped version of the low fidelity function when it doesn't have data. That's what's happening here, right? I'm almost out of time, so I'm not going to discuss much more. I'm just going to say that with the deep GPs, we do that in a non-linear way, meaning that you blend the low fidelity and the high fidelity in a non-linear way within the same function with a graphical model that looks like that, meaning that you are interested in the high fidelity. That's what you really want to show, the high fidelity, right? And the high fidelity doesn't trust observations in the lower fidelities. It doesn't care. It looks only at observations in the high fidelity case. But what's happening is that it also takes input. You can think of it as a GP prior. It gets inputs from the functions that have been learned on the low fidelities. So that's how it's done with the deep GP. And that's the last slide, where it's not only toy data. Here we showed like an experiment where you learn to predict the infection rate of some disease in Africa, and you have high fidelity observations from 2015, and you have low fidelity observations, many, many more from the period before, 2005, I think. And this is a ground truth, and this is the inferred. And you see that kind of the density is matching. And then to also see that we have reasonable uncertainty, we did also DPP sampling using the covariance on the GP, because we shouldn't do Lightning Hypercube for that. And yeah, so that's my final result. I don't know if there's time for questions. Or yeah.